something. Maybe the YouTube channel. Okay, so I guess we'll get going. So we only have a few more days of class. Technically, there's 5 days left, but just like last time, I want to give you'll have like two assignment, like an assignment, and then the group project due on the last day of class, and then also a big programming project due at the end of finals. So I want to give you time where you can come in and just ask me questions again. So we'll try to do the 2 days. You'll get at least one. I can guarantee you that. But we'll try for 2, which means I have a decent amount to cram in. We're not going to go overboard like that one day, but still, we'll get right into it because of that. So last class, we kind of talked about a lighter topic, and I didn't spend too long, and I spent like 20 minutes or something. I introduced the concept of matrices, which are just a grid of numbers. So you've got 3 rows in this case and 3 columns. So this is a 3 by 3 matrix. So number of rows by number of columns when we're notating matrices. And then we said, okay, well, what can we do to these things? Well, we can do row operations, which tells us that we can swap any 2 rows around. So we could say, let's switch those rows. We can multiply any row by a non-zero number, and that's fine. And we can add a multiple of a row to another. Now, this doesn't specify non-zero multiple because you don't need to. If you add 0 times a row to another row, nothing happens. So it's fine. We don't have to specify it. But those are the 3 things that we can do. And I also introduced this concept of row echelon form, which is a sort of nice staircase shape for a matrix. For the furthest left non-zero entry in a row, if we sort of box it in, I'm gonna change that from a 1 to a 5. Who cares? It doesn't have to be 1. So the furthest left non-zero thing better have zeros below it, right? So it looks kind of like this, right? You got this nice little staircase going on, and that's the only specification. We also talked about the augmented matrix. So that is, it looks like this was the notation we used. And all this is saying is, hey, if this represented a system of equations, then this would be what's in front of the first variable in the first equation, what's in front of the second variable in the first equation, what's on the other side of the equal sign. This is the second equation and the third equation, right? And that's all it really was. And we're going to do lots of practice with it, so that's why I didn't really write it down, because today we're going to actually talk about the good way to solve systems of equations using matrix techniques. So we need a quick definition. And this is called, or I guess this is more of a reminder. If we have a matrix, something that looks like if we take it to something that looks like this, we call it the row echelon form of the matrix. So if, actually, maybe I don't even need to write down the definition. That seems like a waste of time. Scratch that. Actually, you just scratched out definition. Now I'm writing it down again. So enjoy scribbles on your sheet. So row reduction is the process of performing row operations to turn a matrix into row echelon form. So what this is saying is, hey, we're going to take something like this, and we're going to perform these steps, only these things, in whatever order we need to make this have this staircase shape. Right? That's all we're doing. So what is the method behind this madness? Well, if we think about the shape that we want to get to, we can actually kind of reverse engineer it a bit. So what we're going to do is we're going to find the leftmost we're basically going to take the top leftmost thing. So take the top leftmost entry and make sure it's a 1 or non-zero. And make it non-zero. So, okay, I guess it's technically possible for you to have like a row of zeros and a column of zeros, but then this would be the top leftmost thing, right? Just the thing that makes sense here. So we want to make this a non-zero number. If it is 0, then that means probably below it is something that's not 0. So swap it, right? And then that becomes not 0. Swap if needed. Okay, cool. Now we're going to make this 1 if possible. Not a strict requirement, but it will make your life much easier if we can do that. Use this to create zeros below it by adding, subtracting multiples. The row. Now we rinse and repeat. So we're going to cover up the top row and repeat. So what I mean by that is in this example, we have a 1 at the top left. Okay, good. Use that to make zeros below it, right? Cover it up. These will be zeros, so rinse and repeat, right? This is the top leftmost thing that's non-zero. Make it a 1 if you can, and rinse and repeat, right? So this is another one of those. This is an algorithm that when I put it in words, it's kind of hard to really see what's going on, but when we actually go through the process, it's much easier to understand. So let's do that. I'm going to write down a matrix. I actually messed this up in... No, I didn't. I messed it up in my notes. Okay, I'm going to do the messed up one because it ended up being interesting. -3, 8, -12. So in my notes, this is actually a 6. So it's a different example now. We're going to do this one, though. And you'll see why. Because it ends up having a twist to it. Okay, so we take a look at this process here. It says, take the top leftmost entry and make it non-zero. Well, we don't have to do anything. It is non-zero. But now the step 2 says, make this a 1 if possible. So there's actually lots of ways to do this if we take this as one step, essentially. I'm actually going to erase that dot and make it one step, because if we want this to be a 1, we could just divide by 4, right? And then we would get a 1 there, and this would be -1/2, and this would be 3/4. I don't know about you, but that seems kind of bad, right? We don't want fractions. Now, this is, there might be, I think there's one exception to this in my notes. You shouldn't get fractions in your final answers when we introduce how to solve systems and that sort of thing. So if you're looking at your actual final answer and you've got a bunch of fractions, you probably made a mistake, because there's no point in me making you deal with fractions, honestly. I'm not here to test your ability to add 1/2 to 3/4, right? I don't care. So that means I don't need to put them in the questions. So your final answers should have no fractions in them. But that doesn't mean every path that leads to the final answer necessarily does not involve fractions. But I will always construct the questions so that there is a path that does not involve fractions. So that means right now we're given a choice, right? We can put any one of these rows up at the top left or up at the top. So surely one of them is more correct. right? We just saw if we divide this by 4, we get fractions. Okay, that's bad. I don't want fractions. So we just think, well, what are the other rows? What can we do to those? We could take this and we could divide it by 2, and then we get 1 minus 1, 1. Oh, that's pretty nice. No fractions, right? So why don't we make that the first row and divide by 2? So let's go ahead and do that. And this is kind of what I mean, right? There's always going to be some kind of path that will let you avoid fractions, because I don't want you to deal with mess. 4 minus 2, 3, minus 3, 8, minus 12. Okay, so all we did was we swapped row 1 and row 2. But now we can do what I said. We're going to say, all right, row 1, divide that by 2. And what are we going to get? 1 minus 1, 1. 4 minus 2, 3. Minus 3, 8, minus 12. All right, cool. So now we do the next step in the process, right? Use this to create zeros below it. Well, how do we create zeros below it? We just add or subtract multiples of this row from these. So we want to use this to make that a 0 and that a 0. Well, if we want to make this a 0, we have to subtract 4 times this from this. So row 2 is going to become row 2 minus 4 row 1, right? That's going to do stuff to these other entries, but the important thing is it makes that a 0. And we do the same thing here. Row 3, that's going to become 3 times this added to that. So, I mean, you can kind of see what we have to do here. If this is a 1, there's not really that much that needs to be done. We just look at this number and put a minus sign in front of it and do that for this row, right? So in this case, it's minus 3. Put a minus sign in front of it, becomes plus 3, right? So that's all we're doing here, if you want sort of a systematic way of doing it. But just remember, we're trying to make zeros here. All right, so what happens? Well, this first row, we didn't do anything to it. This, we know is a 0. We did that on purpose. So what about these other ones? So now this is, you'll see why it's really easy to screw up in linear algebra, because we're about to do mental arithmetic of small numbers, but with lots of minus signs. So this is minus 2 minus 4 times minus 1. And now you can see why that's really easy to screw up. Minus 2, so then minus 4 times minus 1 becomes plus 4. Minus 2 plus 4 is 2. Now, there's nothing wrong with you just doing this on the side if you want. You could look at this and say, okay, I've got minus 2 minus 4 times minus 1. So minus 2 plus 4 is 2, right? So you can just do it on the side if you can't do it in your head. Honestly, it's really hard to do a bunch of this in your head and not make a mistake. So I would say you can write it down if you want. Question? Yeah?
Yeah. So why is it that when you were dividing R1 by 2, you did it on row 1, right?
Yeah.
So if you are doing minus 4, why don't you just do it on row 2? Why do you have to multiply it by minus 1? I don't know if you understand my question.
Not quite. What do you mean?
Okay.
So we're adding the multiple. Minus 4 times this row is being added to this row. Right? So we're going to do minus 4 times this, add to this, minus 4 times this, add to this, minus 4 times this, add to this. Right? The whole row is being added, not an entry.
Okay.
And actually, that's a good question, though, because that is actually a very common mistake. Students will you'll just add like single entries.
Mm-hmm.
No, you have to do it to the whole row all at once. So that's a good question. So yes, you make sure that you're doing it to the whole row. So now this thing is going to come to this, and this thing is going to come to this, right? All at the same time. So now we have 3 minus 4 times 1 is 3 minus 4 is minus 1. And now we do the next row. So this is a 0. I mean, you should check it, but you shouldn't need to because it's just going to be a 0 because that's what we're trying to do on purpose. But now we do the other entries. So this is going to be 8 plus 3 times minus 1. So 8 minus 3 is 5. And then we've got minus 12 plus 3 is minus 9. Okay, and now we just cover up that top row and repeat, right? So we want to make sure that whatever is, on the left, top leftmost that we can reasonably deal with is non-zero. Well, doesn't matter which we pick, it's going to be non-zero. But now we're in a predicament because we make this a 1 if possible. So we could divide this row by 2, and then we'll have a minus 1/2. Well, that sucks. We could swap this up there and divide by 5, but then this would be a 1, but then we have minus 9/5. That's worse. So what could we possibly do? So like I said, there's nothing wrong with doing either of those things, to be honest. There are so many ways to get to the same answer, and if you're just like, screw it, I can't spot whatever trick he wants me to do, and I try to avoid this, but sometimes, like, I write down random numbers, and sometimes it just happens, right? Where some kind of trick will happen, and not on purpose, where we can create a 1 here, but we have to do it in a roundabout way, and we can avoid the fractions. So if we instead look at this and say, hey, if I subtracted 4 from 5, I get a 1, right? So that's, take this and subtract 2 times this row, we'll create a 1 there. And we didn't get a fraction. So we can say row 3 is going to become row 3 minus 2 row 2. So 0, 2, minus 1, those stay the same. So this is going to be 0, 1. So we don't always, our row operations don't always have to be in service of creating a 0. They can do other things, right? So in this case, we created a 1 because that's helpful. Okay, but now we need to figure out what happens here. So it's going to be minus 2 times minus 1 becomes plus 1, or plus 2. So that is minus 7. And all right, cool. Now we do that swap. Row 2 is going to swap with row 3 because now we have that nice convenient 1. 0, 1, minus 7, 0, 2, minus 1. And just to be clear, we're not done yet, right? Because our goal is to create a sort of staircase shape. And we don't have that yet, right? I mean, this is a staircase, but the top leftmost entry, this thing, is where we would actually draw the staircase, and below it is not zeros, right? So we have to keep going. That's how we know we keep going, right? If you find the top leftmost thing from where you just looked at, and it's not zeros below it, we need to do more. Okay, so let's go ahead and do that. So we just want to subtract 2 times this from this. So row 3 will become row 3 minus 2 row 2. 0, 1, minus 7. We didn't touch that. All right, now this is where we change things. This is a 0, again, because we did that on purpose. That was on purpose. So it's minus 2. Minus 1, minus 2 times minus 7. So that's 14. And then the minus 1 is 13. If I didn't make any arithmetic mistakes. But now we look, we got that nice staircase, right? We can't go any further than this. So, a couple things to note here. One, I deliberately do not look at my notes when I do these questions. Why? Because I'm not perfect. Nobody's perfect. I will screw it up. So one, and checks if anyone's paying attention, which, I mean, at 7:30 at night, probably everyone's like asleep, and that's fine. But more importantly, I want you to show that even though I've been doing this for like 20 years, I screw it up too. So the point is, don't get too upset at yourself for making mistakes in this. It's so easy to make little mistakes, and 9 times out of 10, well, let's say 7 times out of 10, it's a little mistake. The other 3 out of 10 times, it's like one of 3 misunderstandings that students are making. It's either the one we talked about, where it's just doing a single entry. It could also be, we say, subtract 4. So instead of subtracting 4 times a row, it's common for students to just subtract 4 from a row. No, that's not what it is. It's subtracting a row from another row. And another one is, don't worry about it. It creates a row of zeros, and it's kind of bad, but it's easy for me to point it out if it comes up. But there's like 3 common mistakes that students make. So it's just something that will be addressed in the work period, right? You'll just be like, Travis, is this right? And I'll be like, you made the mistake. So no, don't do that. And here's why. And you'll be like, okay. And then you won't make the mistake probably. Another thing is this specific thing is not necessarily unique because I said there's multiple ways to get there. So I started with this and swapped it up and divided. If you started with this and made the fractions, you'll get the same shape, but this will probably be a different number, and maybe this is a different number. Who knows, right? You'll have different numbers. The shape will be the same. So this row echelon form is not unique, but we are going to talk about something that is unique. Okay, so why are we talking about this? Well, our goal is to, again, develop a better method for solving equations, right? That's ultimately our goal. So why? To solve equations. And technically, this right here is the ingredients we need. We could solve an equation from here. So you know what? I'm going to cheat. So let's just say we had an extra column there, and this represented a system of equations, right? So this would have come from 4x minus 2y plus 3z equals 0, 2x minus 2y plus 2z equals 0, minus 3x plus 8y minus 12z equals 0, right? This thing would have given us this matrix. And so then we go through all these steps, and actually it doesn't matter what you do here because these are zeros. So if you add any multiple of a 0 to another 0, stays 0. So all of these will have zeros here in this process, which means my final answer has zeros there. So why do we care? Well, at every single step along this way, it still represented this system of equations, right? Because I mentioned in passing, there's 3 things you can do to equations. You could swap them around. That doesn't change your answer. You can multiply an equation by a number, and that doesn't change your answer. And you can add a multiple of equation to another equation, and it won't change your answer. So that's all 3 of these operations that we're doing here. So this will not change our equations at all. But now if we look at this, this still represents a system of equation, still a system. Oh, let's read it off. X minus y plus z equals 0. That's that first equation. Y minus 7z equals 0. And 13z equals 0. Now we're almost there because we got rid of a lot of the messiness of like having to keep track of variables and write down variables and that sort of thing. But we're still kind of not entirely there yet because, okay, this tells us z is 0, but then now I have to plug 0 into all these, and then that tells me what y is, and then I have to plug it in backwards again. That's called back substitution. We already did that, right? So we could continue with back substitution. But we don't want to do that because that's the whole point of this is we want to not have it be messy with equations and stuff like that. So we can do one better than this. So, but we can make an improvement. So we have this nice staircase shape, but what if we made it a little nicer? So if we think we go from the top left down and create zeros below, what if we reverse that process and create zeros above now also, right? So like we go from the top left down and create zeros down, and then go from the bottom right and create zeros up, right? We'll end up with something that looks pretty nice. So that's actually what we want to do, and that's called the reduced row echelon form. I'm jumping around my notes a lot because this was, I really should just redo my notes. So we can insist on what's called reduced row echelon form. So it's called reduced because we're going to make it a little nicer. And it's called reduced row echelon form, which means it's going to have to be a row echelon form, right? We got that nice little staircase going on. So we call it RREF because we talk about it so much. This is the reduced row echelon form. So it satisfies three properties. The first one is take away the reduced. It is a row echelon form. So matrix is in row echelon form. So again, that just means it has the nice staircase where you got zeros all below everything, right? Your concrete foundation is 0. The next thing we need to do is these leading entries, as we call them, those sort of the leftmost non-zero things have to be 1 now. Right here, I said I don't care what the number is. 13 is fine. Now I'm saying no, they have to be 1. Leading entries. So the leftmost non-zero entry in a row has to be 1. That's a new requirement. And the last one is there has to be zeros above those as well. There must be zeros above the leading ones. So that means we would need to put zeros here, here, and here, right? Now it turns out there's also a methodical way to do this. We just get to here and then reverse it, right? So to do this, get to row echelon form. Then, quote unquote, reverse it. So, you're going to instead find the bottom rightmost leading entry. Make it a 1. So that's just going to be whatever that number is, divide by it, right? It's really, so here, I would grab that and I would say divide by 13, done, right? Easy. Okay, now the next step is we're going to use this one we just created to make zeros above. Use this entry, this leading one, to make zeros above. So same exact way, we're going to add or subtract multiples of that row to the things above now. Cover up bottom row and repeat. Right? Just same process. Do it again. So in this case, well, actually, let's actually work with this one. So I'm going to erase this, and we're going to write down that final matrix because step 1 is get it to this form and then continue. So right now we're at this. So we just performed a bunch of steps to get to here. 1 minus 1, 1. Sure, I'll bring the zeros along for the ride. 1 minus 7. 13. So we've got this, right? So let's take a look at what it's telling us to do now. It's saying, okay, now that you've got it to this nice shape, find the bottom rightmost leading entry and make it a 1. This thing, we're going to make it a 1. And we're going to divide it by 13. And we get 1 minus 1, 1. These are all going to be zeros. Nothing happens to them. 0, 0, 1. All right, cool. So next, let's use this one we just created to make those 0. So that's going to be row 2. We're going to take row 3 and add 7 times it. Right? 7 times this plus minus 7 will create 0. And row 1, we're just going to subtract row 3. What's going to happen? This minus that is 0. 7 added to minus 7 is 0. All right. And now we cover up this bottom row, the one we just dealt with, and repeat. So find the bottom rightmost entry that we could deal with, or non-zero entry, I should say. And then make it a 1. Well, it's already a 1, so cool. And then use it to create zeros above. So row 1 will become row 1 plus row 2. I'm just going to add 1 to minus 1. So that adds to that is 0. And now we cover this up and repeat, but there's nothing above this row, so we're done, right? Okay, but now why would we care to do this? Like, what's the value here? Again, let's pretend that all of this represented a system of equations. So that means this still represents a system of equations. So let's go ahead and read it off as that. So this first row is x plus 0y plus 0z equals 0. This is y, so that 0x plus y plus 0z equals 0. This is just z equals 0. So at no point did I actually have to manipulate any equations to do this. I just found out that the only solution that works here is all of the numbers are equal to 0, right? And that solves that very initial thing that we started with. So again, you saw the method we did with like where we were manipulating the equations, it did back substitution and all that stuff, and it was really messy, right? It was tedious, it was messy, it was easy to lose track of things. You had to substitute variables in for other variables and then expand stuff, and it was just and move stuff around. It was very messy. This is just adding and subtracting small-ish numbers to each other, right? That's all we're doing. And then at the very end, we just do this theoretical jump. We're like, hey, this still means a system of equations. Let's write it down. And boom, there's my answer, right? So that's why we care about this, is it actually really helps us do that. So let's actually make that explicit. Let's talk about this method. It actually has a name, which I don't really care about. It doesn't really matter that much. So, method for solving equations. So it's called Gauss-Jordan elimination. So actually, Gauss, physicist / mathematician, discovered this method originally for physics problems. And he said, hey, here's my way of doing it. And it didn't have this improvement, right? So that first version we wrote down here, where we reinterpreted as a system and then had to like substitute variables up again and solve that. That's what he proposed initially. And then Jordan, another mathematician, came along and said, hey, I can make this better. Let's add this extra condition and see what happens. And so he added this condition, and then he was like, see, you don't even have to do anything with the equations anymore. You can just read off the answer. And everyone was like, and he won a Nobel Prize before Nobel Prizes existed or whatever. Point is, it was an important mathematical result. People were happy about it. But I probably won't call it Gauss-Jordan elimination. What I'll probably say is use row reduction to solve this system, right? Because the name doesn't matter, right? It's okay to just call it row reduction. So step one is we're going to state that augmented matrix. Augmented matrix. Can't spell today. So that's this thing. This is always going to be step one for solving any system of equations. So if you do it, you'll probably get 1 mark out of 5. So, hey, there you go. You write down this thing and you got a mark. Hooray. That means like 4 marks are dedicated to the rest of the process. So okay, we've got this matrix. The next step is use row operations to bring this matrix to reduced row echelon form. I'm going to start writing RREF because we end up writing it a lot, so it's nice to get used to it. I will always pronounce what it is, reduced row echelon form, but I'll write RREF. So that's just perform all the operations, basically just do the process we just described. Step 3 is, again, do the process we just described. We're going to reinterpret it as a system of equations. So there's really 3 situations you could find yourself in. 1, a unique solution, in which case you're done already, right? 2, infinite solutions, because remember, you can either have 1 or infinite solutions, in which case we're going to have to do some fiddling, and I'll show you that in an example, where we're going to have to declare some of the variables as quote-unquote free parameters where we can choose them, because that's how we get infinitely many solutions, right? You're given a choice. It can be anything you want, so that's why it's infinite. And then there's a third situation where there's no solutions, but we probably won't even finish this step, and I'll show you in an example that we don't even need to, there's a point where we can just stop and be like, we don't even need to go further. But you could also, if you did accidentally do that, you couldn't spot it, then when you reinterpret it as a system of equations, it will obviously have no solutions, because you'll end up with something that says like 0 = 3. And you're like, that's not possible. So I guess we're done. But those are the 3 steps, right? So, I mean, I summarize it like this, but it is a lot of work. So let's do some examples to show you what it's like. It is one of those things where it's very mechanical. It's very algorithmic. So once you get the hang of it, you could do any of them. Asterisk, you might make an arithmetic mistake, but oh well, that happens. We're not computers. So, that's fine. We're just trying to understand this algorithm at this point. So making little mistakes like that isn't the end of the world. But one little note here is they take up a lot of space. That's why I'm erasing the whole board. So let's solve the following system. Using row reduction. Okay, so I'm just going to write down a system, and it's one we actually did last week. 0, x1 minus x2 equals 1. 3x2 minus 2x3 is equal to minus 1. Okay, so just going into this, I say that these questions will not have fractions in the final answers. Asterisk. This one does. I really need to change it because I say that like except for this one has a fraction in it. But it's that one of those things where I tell myself I'm going to fix it every time I do it, and then something comes up and I just never fix it, and now here I am again where I'm like, I should fix that. So do that 6 times, and maybe eventually it'll get fixed. But we're only at time number 5, so it hasn't been 6 times yet. But the point is, this will have fractions in it. Everything else won't. So I'm just saying that up front. So we take a look at these steps. State the augmented matrix. Okay, great. That's step 1. And this step is, in terms of being a student, is gimme points, 3. Because all we have to do is read off these equations and write it in a matrix. Now, if it helps you, I leave these gaps where the variables are missing, but if it helps you, you could put 0 times that variable there. If you need it, that's fine too, but like I'll usually just leave them blank. But there are zeros there, so 2, 0, 2, do the line, 0. 1, minus 1, 0, 1, 0, 3, minus 2, minus 1. All right, cool. So this is step 1. We've stated that matrix. Now, step 2 is the bulk of the work. It's, all right, now do all these operations to bring it to that nice looking shape. So it's a lot of writing. Once you've done it a few times, again, it's not theoretically very overwhelming or anything. It's just, you feel like the math lady meme, right? You're that, basically, where you're sitting there and you're just like, as like a bunch of math comes at you hard and fast. But it's not challenging. In my experience, most students do not find it challenging. They just find it methodical. I wouldn't even say tedious, because when you do the problems, you're like, really, I'm doing this for marks. It's so easy after you do it a few times. But it is super common. It comes up a lot in so many algorithms. But now we're doing this. So we've forgotten about this equation stuff. We're working on this matrix now. So we want to put a 1 at the top left. So there are 2 choices here. Both of them actually avoid fractions. So my notes, what do my notes do? We're going to do the opposite of my notes. So my notes swap this up to here. So it swaps these 2 things to create a 1 at the top left. We're not going to do that. We're going to divide by 2 on the top row, because that also avoids fractions. Because one thing I want to point out here is that row echelon form is not unique. You could get all kinds of numbers there. This that we're about to do is unique. There's only one form of this. It will always look the same no matter which steps you take. So I'm going to take different steps here, and then you can look in the notes and be like, oh yeah, he got the same thing. So we're going to do row 1 divided by 2. And we're going to get 1, 0, 1. Sound like a computer. Like that. Making sure I didn't copy anything down wrong. Minus 2, minus 1. We just divided by 2. And now we go through our process. We say, okay, I'm going to use this thing I just created up there to create a 0 below it. So we're going to subtract row 1 from row 2. So we didn't touch row 1. That's a 0. We did that on purpose. Minus 1, minus 0. Okay, well, nothing happens. 0 minus 1, that becomes a minus 1. 1 minus 0, that stays the same. And we didn't touch this row. Okay, great. Now, we cover up this top row and repeat. Right? So we say, okay, I want to create a 1, if possible, up at that top left. Well, that's pretty easy. If I just multiply this row by -1, that will become 1, 1, -1, right? So that's a good choice. Again, there's nothing stopping you from moving this up there if you want and dividing by 3. You'll get fractions, but it'll work. But I think this is the easiest way. So we're going to say multiply row 2 by that -1. So what's going to happen here? Didn't do anything to row 1. We did do something to row 2. 1, 1, -1. And we didn't do anything to row 3. All right, and now we do the same process. We're going to say, all right, I just created this nice 1 up here. Use it to turn that into a 0. So row 3 will become row 3 -3 row 2. Running out of space already. You'll see very quickly that's a struggle with linear algebra is you run out of space. I did not change row 1. I did not change row 2. I did change row 3. So this is a 0 because 3 minus 3 times 1 is 0. What about this? -2 minus 3 times 1. So -2 minus 3 is -5. -1 minus 3 times -1. -1 plus 3 is 2. And here is the promised fraction part. Because now we repeat, right? We say, okay, I'm going to cover this up. And, well, at this point, there's not really anything else to do, but I'm going to create a 1 there because I know I need to create a 1. At this point, I do have my nice staircase shape, but I'm going to create a 1 here so that now I can create zeros above, right? So this is going to be row 3 divided by -5. I'm going to divide by that. That is going to create a fraction. But fortunately, we're almost done, so it won't actually be that bad. 0, 0, 1, and -2/5. So yeah, there's a fraction. But now we're going to continue this process. We created our staircase. Now we're working backwards, right? We're going from the bottom right to create zeros above. So we're going to go here, create zeros above. And then we'll go to here, and, well, we would create a 0 above, but there's already a 0 there. So we're going to say row 1. We're going to subtract this from it. 1 minus row 3. And row 2 is row 2 minus row 3. And they're both 1s, so it's easy enough to just subtract them. But what are we going to get? That's a 0, because we did it on purpose. That's a 0, because that's what we wanted. And that's really just these fractions that we have to deal with, and then we're home free. So that's -2/5. So now let's look at this. We're subtracting this from this. So now we got the double negative again. -1 minus 2/5. So -1 plus 2/5 is -3/5. Don't worry about the fractions. I'm not going to test you on this. And then -0 minus -2/5 is +2/5. Like that. And now we're done, right? We've got this nice staircase shape. And we got these nice leading ones. Below it, zeros. Above it, zeros. So that's exactly the shape we want. But now why does this matter? Because we reinterpret as a system of equations. That's the final step. So, what does this say? This first row is an equation. This is x, y, and z. So remember, this is the number that goes in front of x. This is the number that goes in front of y. And that's the number that goes in front of, oh, I used x1, x2, x3. Sorry. So those are our variables, right? This first column is these numbers. then the second column, then the third column, just like this. We went from here to here, now we're going back. So that says x1 equals 2 over 5. x2 equals minus 3 over 5. And x3 equals minus 2 over 5. But now we're done, right? There's nothing left, right? This is the answer. This is, if it said solve the equations, we've done that. I know what x1 is, I know what x2 is, I know what x3 is. Those are the valid solutions. So we could plug these in to make sure. Wait, I think that should be, did I screw up on writing it down? Anyway, no, it's fine. So we can plug these numbers in to these equations and make sure that they work out. So again, kind of hard because they're fractions. So this is 2 over 5. 2 times 2 over 5 is 4 over 5. 2 times minus 2 over 5 is minus 4 over 5. So 4 over 5 minus 4 over 5 is 0, and so on, right? You just check to make sure that the numbers work out. So I'll say that. Plug in and check. And the reason why I'm mentioning that is because these are self-checking, right? So if you worked on one of these problems and you're like, did I get the right answer? I don't know. Well, take this and plug it into here. And again, this is the fraction exception, right? Well, we have fractions here just because that's what's in my notes. But the problems you'll be dealing with will be nice numbers. Like it would be like 1, 2, minus 1. Right, so then you plug in 1, 2, minus 1, 1, 2, minus 1, 1, 2, minus 1, and make sure it works out. And it should, right? That would be the solution. But that's the process, right? And if you flip back to when we did it last week, we did this exact system of equations. This is the answer we got using the messy nonsense technique. Well, it's not nonsense, but it's like gross, right? But this is the answer we got. But it was quite bad. I don't know about you, but at least compared to that method, this is way nicer, right? Because it's just a grid of numbers, no variables making things look ugly. You're just adding and subtracting numbers and swapping stuff around, and it works out real nice, right? So, not so bad, right? Jordan, question?
Just was a little confused about I understand the procedure of it, but you'd go back up and then do a multiplication.
Which step are you talking about?
I think it was step 4. I think it was
This one?
I think so, because you're doing you'll minus from the entire row, but then when you go to the row below it, you'll go times the number, and you'll times it from what's above it.
Yeah, because
do an addition all the way down.
Because we're subtracting 3 times this from this.
Subtracting 3 times.
So there's if it helps you, this is what we're doing. So we're doing this in 2 steps essentially. So we're gonna multiply this row by minus 3. Right? Now add this thing to this thing.
Oh, okay. So
Right.
you're still doing one row, and then you're doing the next row.
Yeah.
And then you're doing the addition after.
So it's minus 3 plus 3 gives me 0. Minus 3 plus minus 2 gives me minus 5. 3 plus minus 1 gives me 2.
Oh, okay. So you just did times on that, and then.
Yeah, but so you can do this on the side if you want, but you have to remember you didn't actually change the row, so go back to the original one. I mean, I guess it's fine if you did do this, but our goal is to make this a 1, so you'd have to go back to it anyway, is kind of what I'm getting at. So it's fine if you want to do it this way, but you'll just create extra work for yourself. But if it helps you understand it, then by all means, go for it. I won't do this. I'll just do these in my head because I only have so much space to work with. But that's essentially what's happening.
Okay.
So this is sort of a, you could do this. So this would be, so we want to do this. This would be row 2 times minus 3. And then this becomes row 3 is row 3 plus row 2. And you just add them together, right? So that's sort of an intermediary step.
Okay.
Don't stress it too much because we're going to do a bunch more examples. If it's any consolation. Because this is the situation where we have a unique solution, right? There's no possible choice here, right? We know what x1 is, we know what this variable is, we know what this variable is. It's these numbers. Nothing else to do, right? So there are 2 other situations that you could find yourself in, though. So I'm going to erase everything because I need the space. So the infinite solutions one is the weirder one, because the reason why it's infinite solutions is we have a choice, essentially. And not we as in like a choice in the process, it's that we have a variable left over that we're free to pick a number, right? It doesn't matter what it is, we still get an answer. So let's take a look at this one. So solve using row reduction. 2x1 plus x3 plus 8x4 equals minus 1 plus 2x2 plus 3x3 plus 3x4. All right, so it's another system of equations. So how do we do it? It doesn't matter. It's the same every time. Step 1, we're going to write down that matrix. Step 2, we're going to go through the process. And step 3, at the very end, we're going to say, hey, that nice looking thing, it's a system of equations. Which one? Let's write it down. So step 1, write this guy down. So we just read it off. 2 minus 4, 1, 8. Draw the slash, minus 1. It's on the other side of the equals. Minus 1, 2, 3, 3, and then a 4. All right, there we go. Boom, 1 mark. Easy. I love getting 1 mark. But now we have to go through the process. So again, there's 2 situations here. You could divide this first row by 2 if you really want to. Bad idea. You're going to get 1/2 there. And sure, go for it if you like fractions. Personally, I'm going to swap this up so that I have a nice looking 1 already. So row 1, let's swap it with row 2. So we basically just swap them around. 2, 3, 3, 4. 2, minus 4, 1, 8, minus 1. All right. 1.5 marks now. We're really adding them up. Now let's multiply this by minus 1 times minus 1, just to turn that into a plus 1, because we're going to need to do that in the end anyway. Two minus 4, 1, 8, minus 1. Now, there is something you can do here. I wouldn't advocate for it. I'm just telling you it's okay. The reason why I wouldn't advocate it is it's so easy to screw it up, because doing this can lead to you creating a row of zeros every time, which will give you absolutely the wrong answer. I will give you almost nothing for it. So be very careful with this. But if you want, you can do multiple things at once. So look at this. We're swapping these 2 rows, and then we're multiplying this by minus 1. So you could do that at the same time. But be very careful if you do that. I won't do that on the boards because I think it's really confusing. Because do I swap them and then multiply, or do I multiply and swap them? Well, you do them simultaneously, right? So it's very confusing. But that's really what happened here. So if you want to do it that way, go for it. But I think it just complicates it. This is me just saying that's okay if you want to do it that way. I won't, though. So now we're here.
Sorry.
Yep.
But can you multiply row 2 by -1 before you swap it?
That'd be fine. Yep, you could do it in either order. That would be fine. So that kind of goes back to the point of there's lots of different ways to do these, and you should get to the same answer. So with this method, if you and your friend are sitting there and you're like, here's what I got, and you're like, here's what I got, they should look the same. Even if you look and you're like, wait, you did it a totally different way. That's fine. That can happen, right? That actually probably, well, I don't want to say probably because the path to avoid fractions is usually staring you in the face, and if you do it that way, it'll work out, and everyone will do it that way. So our goal, we got this nice happy 1. Use it to get rid of that 2. So row 2 minus 2 times row 1. So we've got 1 minus 2 minus 3 minus 3 minus 4. We didn't touch that one. But now we got to do some math. So this is a 0. Okay. Now it's -4, and we subtract 2 times -2. So -2 times -2 becomes +4. -4 plus 4, 0. Again, you could do this on the side if you want. So I just said, okay, -4 minus the 2 here times -2. That's -4 plus 4, which is 0. Right? If you're comfortable doing it on the side, go for it. Right? I won't discourage it. Better to write down extra information and be sure than to try and do it in your head and muck it up. I don't penalize too much for arithmetic mistakes for what it's worth, but you can avoid it. Okay, 1 minus 2 times -3 minus 2 times -3 is +6. So 1 plus 6 is 7. 8 minus 2 times -3 minus 2 times -3 is 6. 8 plus 6 is 14. -1 minus 2 times -4 minus 2 times -4 is 8. -1 is 7. I think they're like the biggest the numbers will probably get. 14. It's not a very big number, but trying to do it in your head can get a little. Okay, so now we repeat the process. We created a 1 up here. We use it to make a 0 right below it. Cover that up and repeat. Although there's not a whole lot more left to do because there's no zeros to create below it. So we just take this row and make a 1 in front of it. So row 2 divided by 7. -3, -3, -4. 1, 2, 1. Right, we just divided that row by 7. Oh, look at that. We got our nice 1s. We got our 1s and we got our staircase. So, okay, that's a good sign already. So now the next step of the process is we want to take these and create zeros above. Well, there's no 0 above that, so we don't have to do anything. So we've only got one more step. So row 1, row 1. So that's a -3. 3 times that will get rid of it. 1 -2. Zeros there. That. So we turn that into a 0 on purpose, right? 3 times 1 added to -3 gives us 0. 3 times 2, which is 6, added to -3 gives us 3. 3 times 1 added to -4 gives us -1. See? So now we got our nice leading 1s. Below it, a 0. Above it, a 0. Good shape, right? This is what we want. So this is that RREF. And so now we do step 3, which is reinterpret it as a system. This means equations. So we take this. So it's x1 minus 2x2 plus 0x3 plus 3x4 equals -1, and x3 plus 2x4 equals 1. This looks a little different from the unique equations, or unique solution, particularly because we've got 2 equations and 4 variables, right? So this is what's called an overdetermined system, right? We have some extra stuff here. And what this really means is we're free to choose some of these things, and we'll get an answer either way. So, how do we determine that? Well, let's take a look at this right here, this nice looking matrix. And remember, these columns, they represent the variables, right? This is the stuff that goes in front of the first variable. This is the stuff that goes in front of the second, the third, and the fourth. So these so-called leading ones correspond to the variable x1 and x3, right? So what about these ones? They don't have those leading ones in front of them, right? They're just kind of stranded there. Nothing really happens. So these are what we call free variables. And the way you can see them is no leading one in their column. Right? So we've got this column here, there's a leading one. This column here, there's a leading one. So the free variables, there's no leading one here, right? We just kind of go past it in the staircase. Same thing here. We go past it. We don't make a jump down. So this, well, they're not really x. They're free variables, right? They're not wrong per se. So maybe it's also a check mark, but they're different, right? So what that really, the reason why we choose free variables is we are free to choose them to be whatever numbers we want. In our solution, we don't choose a number because really our job was solve the equations. Someone else comes along and says, you know what, I like x2 to be 3. And then someone else comes along and says, no, I want it to be 1. Both are correct. That's fine. So what we have to do is an extra step here, is we solve this thing in terms of our leading variables. And what that means is you just move the free variables over. So you just take these and move them over. So that's going to be x1 equals, and now you see, this is why we do this, because now x1 is just determined by choices. x1 equals 2x2 minus 3x4 minus 1. It doesn't matter which order you write them in. x3 is, move that over, 1 minus 2x4. And so then the extra piece of information we'd write down is we need to say, hey, you get to choose x2 and x4. So we would just say x2 equals free, and x4 also equals free. Another way to do this, some people prefer this, is you can actually do a sort of quote-unquote physics thing. So you could say, all right, we got my x1, x2, x3, and x4. I'm going to assign parameters to my free variables. So s and t, like physics, right? Time and stuff like that. And then you just replace these variables with that, so it's more obvious that you're free to choose them. So 2s minus 3t minus 1, and 1 minus 2t. Both of these are fine. You can do whichever one you prefer. This is probably easier, though, because you don't have to think about it. You just move the stuff over and then just, you'll write down x1 and you'll write down x3, and then you're like, I have 2 variables, and you just say x1, x2, x4 free, right? And that indicates, hey, you could pick them to be whatever you want. So in terms of doing this, if you did all of this, and then you got to here and you're like, that's free variable stuff, I didn't get it. If you didn't write this down, you got like 4.5 out of 5. Like, honestly, this step here, not moving the variables along, but just reinterpreting this as a system of equations, is no different than the other one, right? You look at this and you write down what you see. It's the moving stuff over that's the extra step, and that's probably worth like 0.5 marks, honestly. I don't really care that much, because There's one extra step here, literally one step, and it's the same. So I wouldn't put a lot of emphasis on that. So my point is, the bulk of the work is going through these row operations. That's what I care about. Now, if we were writing a programming algorithm, then we would probably already need to determine if we have free variables before we even solve things, because this would sort of be like a branching point, right? We would need to do something different in this case. Like for that first one, we would just return the numbers. In this case, we're going to have to return some parameters and stuff like that. It's a bit more involved. Okay, one last example, because we just did unique solution and infinite solutions. There's one more. It's very, very easy though. You'll see, because basically it stares you in the face. So I don't need the full board for this because it's kind of a short one. So if you haven't finished writing, I'll leave it. Some of this available. Like that. That's probably enough space. So we're going to solve this. Plus 2x2 plus 0, 2x plus 3 plus 1, x1 minus 8x2 equals 3. Process is the same, right? We got this. Write down the matrix. 1, 2, 0, 2, 3, minus 1, minus 4, minus 8, 3. Bam, 1 mark. All right, we're batting 100 today. So now we just need to perform our row operations. So step 1, put a 1 at the top left. Oh, all right, cool. So now just use that 1 to make zeros below it. So row 2 will become row 2 minus 2 row 1. Row 3 is going to be row 3 plus 4 row 1. All right, so we don't change this row. So this is going to become a 0. We did that on purpose. So now we just need to figure out these entries. 3 minus 2 times 2 is minus 4. 3 minus 4 is minus 1. Minus 1 minus 2 times 0 is minus 1. Don't have to do anything there. Minus 8 minus 2 times 4 is minus 12. And minus 0, nothing happens. All right, cool. Rinse and repeat. Cover that up. Make that a 1. Well, we just have to multiply by minus 1. That's not too bad. So what do we get? 1, 2, 0, 0, 1, 1. Cool. Almost there. We got these nice leading ones, but this is the one we just made. So let's make a 0 below it. So that's row 3. Is row 3 plus 12, row 2. I feel like I made a mistake there, but did I? Oh, yeah. I think these numbers are wrong, actually. Sorry. This is what I mean. It's so easy to make arithmetic mistakes. So we might not have even needed to go this far, because it's 4 times this added to this. I did minus 2 times that. So minus 8 plus 4 times 2, minus 8 plus 8 is actually 0. And 3 plus 4 times 0 is 3. All right. So, okay. But now we have a nice little staircase. So we could keep going. But there's something I want to point out here. At every step of this way, it still represents a system of equations. So let's just take a look at what this system of equations is telling us. So it's x1 plus 2x2 equals 0. Minus x1 equals, minus x2 equals minus 1. And 0x1 plus 0x2, which is 0, equals 3. That's impossible, right? Nothing we can choose for x1 and 2 will make this true. So this is no solutions. So you can stop as soon as you run into something that looks like this. If you've got a row of zeros, who cares how many there are? And then you've got a non-zero number. Just stop and just say no solutions, right? You're done. Right? You could just stop right there. So those are the three situations, right? No solutions is easy to spot. You spot, there's nothing wrong with if you just keep going and then reduce it to row echelon form. It'll still work out. You'll still make the same conclusion. Your last row will be 0 equals 1. And you'll be like, hey, wait a minute. And you probably could have stopped earlier. But the point is the process is the same for every single one of these, right? At this point, I mean, you need practice, but you now have the tools to solve any system of equations. That's a linear system of equations. This process will do it every time, no matter how complicated they are. Now, obviously, I'm not, well, I like to think that I'm not someone who tortures you on purpose. So I see that. So reasonable numbers of equations and variables. So like 4 variables and at most like 3 equations, maybe 4 if they're really simple. Because there's no point in me saying, all right, you got 13 variables and 16 equations. It's like, Travis, why? Writing down the matrix takes up the whole screen. Like, really? Like, yeah, no, I don't need to do that, right? It doesn't have to be very big for me to test your ability and make you go through a few steps. So anyway, that's all I have for this. So on Wednesday, I'm going to give you lots of practice. I might even open with an example to just refresh you. I'll make up a random one on the spot with some direction. I'll make sure that there's not, by on the spot, I mean right before class, I'm just going to construct one. There shouldn't be fractions. And then I'll be like, okay, and now you go do it. Here's the quiz. The quiz is going to be do it. And then we're going to follow the same pattern we have been throughout the rest of the course. You know, we introduced that logical operators. And then we said, okay, what can we do with them? What sort of tricks can we do? And then we said, okay, we got these sets. What can we do to them? Okay, we've got these vectors. What can we do to them? Well, we've got these matrices. What can we do to them? Turns out we can add them and we can subtract them and we can multiply them. And that's the interesting one. Because throughout the whole course, I'd write, okay, yeah, I'm going to write down the commutative property and the associative property. And I'd be like, can't take these for granted. They're not always true. We're finally bumping into one where they're not. Matrix multiplication is not commutative. A times B is not the same thing as B times A, almost ever, actually. So it's very poorly behaved, and there's some interesting consequences from it. We'll talk about that. But with that, that's all for today. And so, oh yeah, go ahead.
Can you please explain the no solution bits, like the last bit after the 0 is equal to 3?
So right here.
Yeah. Like,
Well, so what values of x1 and x2 can I choose so that 0 equals 3?
no.
Yeah, nothing. It doesn't matter what I pick here. I'm going to be saying 0 equals 3, which is not true. So that's why we know there's no solutions, right? We found something that's essentially nonsense, where in doing this process, it said, hey, 0 has to equal 3. And you're like, okay, well, that's not going to happen. So that means nothing I pick matters. So we don't have to continue, right? And that's why there's no solutions, because it's essentially a contradiction. It's just, it doesn't make sense. Yeah. Okay. I will see you all on Wednesday.